Alright, today we're going to look at nature of roots of quadratic equations. Now for a quadratic equation, a property of the quadratic equation is the discriminant, given by b squared minus 4ac. So this discriminant comes about when we try to solve the quadratic equation ax squared plus bx plus c equals to 0 using the general formula given by x equals to negative b plus minus square root b squared minus 4ac over 2a. So in the square root you see the discriminant and it affects the nature of roots of the equation. So for example, if b squared minus 4ac is bigger than 0, obviously you can take square roots. And given plus and minus, you always end up with two real and distinct roots. If b squared minus 4ac is equal to 0, then we have negative b over 2a, which just gives us two real or equal roots, which is the same as having one root which is repeated. On the other hand, if b squared minus 4ac is negative, which means that I cannot take square root and hence the equation has no real roots. Alright, so this is how the discriminant comes about. So with that in mind, graphically, what it means that if b squared minus 4ac is bigger than 0 and I have two real and distinct roots, the quadratic graph should cut the x-axis twice, right? Because these 2 points will be the roots of the equation. If b squared minus 4ac is equals to 0, I have repeated roots. It means that the quadratic curve can only touch the x-axis at one point, or in other words, the curve is tangent to the x-axis. In the last case, when b squared minus 4ac is less than 0, I have no roots, or in other words, the curve doesn't even touch the x-axis. If it does not touch it, then obviously there are no roots. Now let's look at an example. Example 1. Find the range of values for k for which 2x squared plus 5x plus 3 minus k equals to 0 has two real and distinct roots, for part A. For part B, two real and equal roots, and for part C, no real roots. So what does this mean? Now if I consider the graph of the equation y equals to 2x squared plus 5x plus 3 minus k. Let's see how this looks like. So this is the equation of the quadratic curve, and I have the values of k. In this case, k is now equals to 2.4. So we see that the curve cuts the x-axis at 2 points. So there are two distinct real roots. But if I vary the value of k, as k decreases, the graph is now above the x-axis, which means that it has no real roots. Right? So you can see the effect on k on the quadratic curve. So of course, if k just touches, in this case it touches the x-axis, it has only one real root or two equal real roots. So we need to find out this range of values of k, for different cases in the question. Now coming back to this, all we need to do is to look at the discriminant. For this equation, the discriminant is given by b squared minus 4ac. So b squared is 5 squared minus 4ac. C is 3 minus k. Alright, since k is a constant, and we view this as 2x squared plus 5x plus 3 minus k equals to 0. We have a, b, and c. So this gives me 25 minus 24 plus 8k. In order Okay, so we have 1 plus 8k. So in order to have two real and distinct roots, 1 plus 8k must be strictly bigger than 0. So k must be bigger than negative 1 over 8. For b, to have two real and equal roots, I just set the discriminant b squared minus 4ac to be equals to 0. But from part A, we already found a discriminant, which is 1 plus 8k. So k is equals to negative 1 over 8. In the last case, b squared minus 4ac is less than 0 since it has no real roots. So in this case, 1 plus 8k is less than 0. Hence, k is less than negative 1 over 8. Right. So in these three parts, we have three different ranges of values for k, okay, which will determine the nature of its roots. So let's do a quick double check. So if k is equals to negative 1 over 8, which is about 0.125. Okay, 0.125 is about here. Okay, so you see negative 0.1 is already going to touch slightly. Alright, so around this region, okay, it cuts the axis. Alright, as I increase k, there will always be two distinct real roots. However, if k is less than negative 1 over 8, the graph doesn't cut the axis, so we have no real roots. Let's look at another example. Show that the equation x squared plus kx equals to 4 minus 2k has real roots for all real values of k. Okay, in other words, no matter what value of k I put in as the constant, okay, the final equation will always have real roots. But in other words, when the quadratic equation has real roots, okay, for all real values, this would mean that the discriminant b squared minus 4ac is always positive or equals to 0 for any real value k. Okay, so regardless of the value k, the discriminant should be bigger than or equals to 0. And this is something that we need to prove. Okay, so let's show this now. So first of all, let's write down the equation and group them so that I can find the coefficients a, b, and c. So I rearrange it to get x squared plus k plus 2, sorry, okay, x squared plus kx minus minus 4 plus 2k equals to 0, right? So x squared plus kx plus 2k minus 4 equals to 0. So from here I know that a equals to 1, b equals to k, c equals to 2k minus 4. So the discriminant is b squared minus 4ac, which gives me k squared minus 4, 2k minus 4. Okay. So let's simplify this. I get k squared minus 8k plus 16. But at this step, how do I know that k squared minus 8k plus 16 will give me a positive number or 0 for any value of k? Well, it so happens that k squared minus 8k plus 16 is a perfect square. And perfect square must be bigger than or equal to 0 for all real values. Okay, so regardless of the value of k, the discriminant is bigger than or equals to 0, so show. So let's look at the graph and see what's going on. Okay, I have this graph, okay, the graph of the quadratic curve. When I vary the value of k, no matter how I increase or decrease it, okay, the graph always cuts the axis at least one point.